This is ASFurther Pure Maths. We're in Unit 4. We're looking at vectors, and this is 4.10, which is the scalar product form of the equation of a plane. So here's our plane here. There's a point A, there's a point R, there's our origin, so that'll be the vector A taking you to there, there's a vector R taking you there, and N then is going to be our normal vector then coming out of that plane. So a normal acts in perpendicular then to the plane. So the point A with position vector A lies in the given plane. The vector N is perpendicular to the plane. The point R with position vector R is any other point in the plane. Then AR, how do you get from here to here? Minus A plus R, as ever, so it's R minus A. Since A and R lie in the given plane, then AR must lie in the plane, so that line lies in the plane. But if N is perpendicular to the plane, then the directions of N and AR must be perpendicular. This is perpendicular to the plane, this is on the plane, so those two lines then are perpendicular. However, if two vectors are perpendicular, then their scalar product is 0. We know that. So that means R minus A, which is this line here, and N, which is this line here. So the dot product of those two, that's what the dot's for, equals 0. Multiplying out your brackets, you get R dot N minus A dot N equals 0. Or if you want then R dot N equals A dot N. And if AN equals P, then an equation of the plane is R dot N equals P. Given that a plane contains a point with position vector A, that R is a position vector of any other point in the plane, and that N is perpendicular to the plane, the scalar product form of the equation of the plane is R dot N equals P, where P equals A dot N. As ever with this, it hopefully comes a little bit more clear whenever we start to look at examples. So let's look at example 1. We're going to change some of these values here because I haven't quite worked out. I think this one, can we change it to minus I plus j, I think, minus k. So a point A with position vector lies in the plane. The vector minus I plus j minus k is perpendicular to the plane. Find an equation of the plane in scalar product form. So that's just what we had up here. And then in Cartesian forms, we'll explain a bit more about that in a second. So part A. We know that R excuse me, minus A dot N equals 0. So in this case, we're going to have R take away 1 minus 2, 1 dot minus 1, 1 minus 1 equals 0. And multiplying this out, we're going to have then R dot minus 1, 1 minus 1 equals, so again I'm multiplying out your brackets here and taking this over the other side, so it's 1 minus 2, 1 minus 1, 1 minus 1. So R dot minus 1, 1 minus 1 equals, and this is just the dot product here, so we're just doing this times this, so minus 1 minus 2 minus 1 minus 1 minus 2 minus 1, and so R dot minus 1, 1 equals minus 4 is an equation of the plane in scalar product form. So that's part A. Second part then is in Cartesian form. So I'm just going to use what we've just worked out there really. This is part B. Part B, if we're going to let R, which is our standard point, it's x I plus y j plus z k. So if R equals that, then xi, right, plus yj plus zk, take away minus I plus j minus k equals minus 4. So that's obviously the dot product term. That's r dot n equals p. So that's where that's come from. So this is this here. There's your r. There's your dot. There's your minus 1, 1, 1. Sorry, minus 1, 1, minus 1. And there then is your minus 4. So if we do the dot product of those, I minus I, that is going to give us minus x plus y minus z equals minus 4. And I would rearrange that. I'd take everything over to this side, everything over to this side, just to get rid of more minuses. X minus y plus z equals 4. And that then is Cartesian form then out of an equation of a plane. It's very straightforward really. If you kind of look, if you have the r dot n form of it, let's take away, look, I can tell straight away that that's just going to be then minus x plus y minus z is minus 4. And that's it, kind of straight from that. If you have the equation of the plane in this form here, it's very, very easy then to get the Cartesian version of that. Okay, example 2 then. Show that the line with equation r equals I plus 2j plus k plus lambda 2i minus j, where lambda is a scale parameter, lies in the plane with equation that. So this is our equation of the line. That's our first form. That's just a plus lambda b, nice and straightforward. And then here's our r dot n equals p form. So we need to show that this line lies in this plane here. So here's the way we're going to do it. This diagram, I don't know if it's worth doing or not. There's your plane. And if the line lies in it, one way of showing that is to find 2 points on the line. And if both of those points also lie in the plane, then the line must lie in the plane. I hope that makes sense. So that's what we're going to do. So do we know any points that are on this? Of course we do. We know we're A. So that's 1, 2, 1. So let's write that down and see if we can see if that one actually works in the plane. So now the line passes through the point. One, 2, 1. That means then 1, 2, 1 dot 1 minus 2, 2. So what am I doing here? I'm now subbing the point 1, 2, 1 in instead of r, and I'm finding the dot product. If it equals minus 1, then it lies on the plane. So that's going to be 1 minus 4 plus 2, and that equals minus 1. So that's good news. Therefore, 1, 2, 1 lies on the plane. How do we find another point that's on this line here? Well, the way we generate points for this is we give in different values for lambda. So if we make it nice and straightforward and just let lambda equals 1, that's going to give us another point. So to find another point on the plane, let lambda equal 1. So that means we're going to have r equals 1, 2, 1 plus 1 upon 2, that's 1j, 0. So that's going to give us the point 3, 3, 1. So that's another point on the line. If we can show that this one also lies on the plane, then the line must lie on the plane. So we go 3, 3, 1. This is subbing it in now to the plane formula. What's it going to give us? 3 minus 6 plus 2, that equals minus 1. So it works. Therefore, this point is also on the line, and plane, hence the line lies in the plane.